I think we left off last time at the power calculations section. So we went through and we said that power dissipated in a resistive circuit, or power in a circuit in general, power in any circuit is equal to basically the voltage multiplied by the current, and then we used Ohm's law over here to substitute, and we found different ways to express the power equation. Right, so if I substitute for V in this equation, so I remove the V equals R times I, and so I end up with R times I squared, right? Or if I solve for I have I equals to V over R, so I substitute for I over here, so I end up with having P equals V squared over R. Right, so there are many ways to write the power equation depending on what variables you have. Sometimes you will have voltages known, so you use one equation. Sometimes you'll have currents known, so you'll use the other equation. So we'll spend some time doing some examples on everything we covered so far. So we talked about resistivity and how to calculate resistance of a conductor, and we said that the resistance of a conductor is equal to rho, which is the resistivity, multiplied by the length divided by the area of the conductor. So the larger the diameter, obviously, or the larger the cross-sectional area of the conductor which current is flowing through, the lower the resistance that we have, which is why you will find the overhead transmission lines, big cables without an insulating jack around them, they're just hanging up there. They need to be low resistances, because otherwise we will be burning all this power that we're transmitting through the power system here. So in a distribution system, we don't have an option. We have to live with smaller wires because we have to put them behind the walls, under the ground, above the ceiling. So we cannot have all of these lights, for example, fed from huge diameter cables because they're low resistance. So it's a cost issue, it's a weight issue that we cannot basically work with. So there is a need to always calculate the resistance of the conductor and optimize that based on what application you are. Are you a distribution application? Are you a transmission application? And of course, the value of the resistance will affect the power loss in the system. So we will next, I think, calculate the power loss in the system, in the resistor. Yeah. So the value of the resistor will depend, or the equation for the value of the resistance is rho L over A. So given you have a resistance, given a copper wire having a diameter of 2.05 millimeters and the length of 10 meters, and the resistivity of copper is 1.72 times 10 to the minus 8 ohm meters. So they want to calculate the resistance of that, so it's a direct substitution in the equation. So the resistivity is this rho over here, the length in meters, and obviously the area you have to calculate in meters squared. So if you calculate the area in meters squared and do a direct substitution, you will end up with the value of resistance for the conductor. So they converted they made sure that the area is in meters squared. Okay, so you'd have to convert the radius or the diameter that you have to meters. So just pay attention to the units and it should be fine. Direct substitution. Another example, we would like to calculate the power dissipated in a resistor. You have a power. You have the power that the resistor is rated for. So you buy resistors in different power ratings. So your cell phone has resistors. Your resistors in the cell phone are one ohm, different values, right? But the power rating of the resistance that's used on a cell phone board is very different than the power rating of the resistance that is used in a power supply for a laptop. Your adapter power supply is very different from the value of the resistance used in a large power drive circuit. It's a very different power dissipation value, but the resistance is the same. So it's the same 1 ohm resistance here, 1 ohm resistance here, 1 ohm resistance here. However, it's rated for different power levels. And so that's when you go and buy resistors, you have to buy them for a certain power rating. Quarter watt, half watt, 1 watt, 5 watts. And I've seen resistors burn, so you smell them burning. They would just small explosion and they will burn. So because you selected the wrong power rating, even though you selected the same value of resistance. So you have a 1 kilo ohm resistance rated at 0.25 watts. Find the current through and the voltage across the resistor. So you're given what? You're given the value of the resistance and its power rating, right? From the power equation, we know that power is equal to I squared R, and power is equal to V squared over R. I'm not given the voltage here. I'm given the power and the value of resistance. So what I can do is I can use this equation. Then they're asking for to find the current through it and the voltage across it. So I can either use this equation, power equals Ri squared, and then from there find the current, or I can use this equation and from here find the voltage, right? And they found the current from here and the voltage for here. But you can also do what? You can, after finding the current, you know power and you know current, you can go back to the P equals V times I equation and just you find voltage from there, right? So it does not matter which equation you use. I mean, they're all one equation. There are only two equations in electrical engineering. Ohm's law, V equals I times the impedance. In this case, we talk about resistive DC circuit, so V equals I times R. And power equals V times I. Really, that's all electrical engineering. They don't study too much. I don't know why they complicate it. But it's really these two equations. But then when you use these equations in an AC circuit, it's a bit more involved. You have magnitudes and angles. So instead of one single equation, we have a complex equation with magnitude and angle. But that's electrical engineering in a nutshell. So this is one example of that application of the power equation. Next, what we'll do is try to solve some simple circuits and then expand a little bit. So we talked about the direction or the polarity of current in a circuit, etc. So we want to solve some simple circuits and build some larger circuits and start solving them. So this is an example. Solve for voltages and currents in the circuit. The circuit is this circuit here. So I have a voltage source with this polarity, the plus here, the negative here, with a resistor across it in parallel, right? So what is the voltage polarity? So don't look at B, C, and D, please. Okay? So what is the voltage polarity across the resistor? The resistor is in parallel with the source. So we said if two elements are in parallel, they will carry the same voltage, right? So now the voltage polarity is defined by my voltage source, right? So my voltage across the resistor will have a positive on top here and a negative below here, and that's what we have in the first step. So you define your polarity of voltage across the resistor. We know the resistor is an element that only dissipates or absorbs energy. So if you go to our passive sign notation, right, we said that the resistor or an element that absorbs power or absorbs energy will have current flowing into the positive node, right? So I can now draw IR flowing into the positive node this way. And then finally, the IR is flowing through here, and this is a series circuit, so this is a circuit where current has to flow in this circuit in the same direction. Current will not flow in one direction, in an opposite direction, and then the other, not in the same loop. Current will have to flow in the same direction. So this helps us define the direction for current here as well. And we also know that this is a source. It's a source that is supplying power. Source that is supplying power, current will go out of the positive terminal, right? Any element that is supplying power, current will be flowing out of the positive node. So it just confirms the fact that we also chose the proper notation for or proper direction for the sign of or the direction of current to the resistor, right? So this is a very simple example, but it helps us review these notations that we talked about, right? And then now they want you to find the voltages in the current, right? So after we put all the notations and the directions of current, etc., let's see what the voltages and currents are in the resistor. So the polarity is defined by the positive and negative as we discussed. Since this resistor is in parallel with this source, then the voltage across the resistor is equal to 10 volts, which is the source voltage, right? Another way we can do it is what? That's something else we studied, or we talked about last time, that if we don't know this idea of parallel, we said that the voltage around the closed loop, using Kirchhoff voltage law, if we sum up the voltages around the closed loop, the sum will be 0, right? So here, I start here at this node. You start from one node, you come back to the same node and go around the loop. You start from this node, I see a minus sign first. So minus 10 plus VR is equal to 0. So minus 10 plus VR is equal to 0, so you bring minus 10 on the other side, so VR is equal to 10. So your Kirchhoff voltage law or the fact that they're parallel just tells you the solution. Now you have the voltage across a resistor and the value of the resistance. I want to know, and you've defined the polarity of current through it. So how would you find the current flowing through the resistor? V equals IR from Ohm's law, right? So then here IR is equal to V divided by the resistance, which is 2 amps, right? So 10 volts divided by 5 ohm is 2 amps. This is slightly more involved. It also includes a dependent source. We talked about dependent sources, and we gave their analogy last time when we introduced the idea of dependent sources. So solve for the source voltage. So here, what is unknown is the actual source voltage. So it's like you have a chemical, you have a flow loop or a circuit, a fluid circuit, and you would like to define what pump pressure to use, right? So you would go back and look at your circuit. You have to understand your circuit to be able to understand what pump pressure to choose. That's sort of the same thing. And we will, whenever you have a bigger circuit, start looking from away from the source first and come closer to the source. So now let's see what we have. We have a resistor here that they've given us the polarity of current through. So if they gave us the value of the resistance, they gave us the voltage across the resistance, right? So if they gave us the voltage across the resistance, and we know that the resistance absorbs power. So since we know the resistance absorbs power, and they've defined the polarity of voltage across the resistance, then we know current will flow into the positive node, right? So current is flowing into the positive node in the resistor. The resistor value is 5 ohms. The voltage is 15 volts. So what is the current flowing into the resistor? And V equals IR. So 15 volts is equal to the current flowing through multiplied by the resistance. So 15 divided by 5 will be 3 amps. So 3 amps is the current flowing in this. IY is equal to 3 amps. Right? So we know a lot about what's happening here now. Then let's see what's happening here. Here we have a dependent. What is this? A dependent voltage or a dependent current source? Dependent current source. We said the dependent voltage source would be the same triangle, but with polarity signs plus and minus inside. And dependent current source would be the same diamond. Sorry, not a triangle. Diamond. I mix up my shapes a little bit. So it's the same diamond with an arrow inside, indicating the polarity of the current flowing through. Here they have indicated the polarity of the current. But if Ix happens to be negative, what does this mean? Then in reality the current is flowing in the other direction, right? So here it will depend on what we solve for Ix, what we find Ix equal to, right? We don't know. But so we know that this is just a dependent current source pushing current into this node, right? This is a junction now of your fluid circuit. Whatever's coming into the junction is whatever's equal to whatever's coming out of the junction, right? So I know that current polarity here is equal to this. And they have assumed, let's assume a current polarity equal to looking in this direction, looking into the same direction as the arrow, so going into the node, equal to 0.5x. So 0.5x is coming into the node, Iy is coming out of the node, and they said that Ix is coming, you will assume Ix coming into the node. Yes. The what? Excuse me? Current flow in the resistor? The variable, the dependent current source. A dependent current source, we will assume that it will have a direction equal to, as dictated by the arrow, for now. But what if we solve and we find, and they told us that this is Ix. But if we solve this circuit and find Ix to be negative somehow, right? If we solve this circuit and find Ix to be negative, then you just tell me that the actual polarity is opposite of this. Right? But you keep it the same. You have to assume some polarity, and then solve the circuit. Yeah, the current provided by this source depends on the current flowing in this resistor. Right? It's like having a control circuit in your fluid application. So you have the flow in one branch depends on the temperature of your boiler, right? I made it depend on the temperature of the boiler, or it depends on the flow in another branch, right? Uh, just a choke in there, for example, that is controlling the flow. Yes, sir. An ideal current source, no. So ideal current source has no impedance at all. It's has no voltage across it. There's no resistance. There's nothing across it. So if you look at the voltage here, is equal to what? What is the voltage across the current source equal to? Equal to what? X? No, not Vs. It's equal to, remember, only elements that are exactly in parallel have equal voltage, right? So this current source is in parallel to this resistor and Vs, and is also parallel to this resistor, right? So the voltage across this current source is 15 volts because it's in parallel with the resistor, right? Or it is also equal to the sum of these two, right? We have to go Kirchhoff voltage law around the loop, right? So we start a loop here. This would be a loop here, right? But this loop here, there's no current voltage drop across this current source, right? So if we start here, for example, we know that we will have minus Vs, right? Plus Vx, and then what? This current source has a voltage drop across it equal to 15 volts with the same polarity as the parallel branch, right? So minus Vs plus Vx plus 15 volts is equal to 0, right? So minus Vs plus Vx plus 15 volts is equal to 0 in this case. This will be one equation that we will use. In the next slide, we will do that. But we still don't have enough information to solve the circuit because here minus Vs plus Vx plus 15 volts equals 0, we have two unknowns. So we still need to find a solution to this one. Exactly. So, which is the missing thing that we wanted to find. One second. Because again, the current source is in parallel with this resistor. So the voltage polarity for any parallel element is the same. Any parallel elements have the same voltage magnitude and polarity across them. Otherwise, they cannot be in parallel. Right? If they're different somehow, if two elements that are in parallel have a different voltage across them. One is trying to push current into the other. Right? If there's any voltage difference, current will flow. Anytime you have a voltage difference, current will flow. Right? So two parallel elements have equal voltage across them. Okay? So as we were just discussing, this is we know that for us to find the objective is to find Vs. So if you go around this loop, we cannot do it because let's go around this loop starting from this node. So still minus Vs plus Vx plus 15 volts is equal to 0, two unknowns. Same thing around this loop, which has the current source, it's exactly the same. So we have to find another condition. So one way to find it is using Kirchhoff's current law around this node. We know Iy already. We calculated Iy. So this current is coming into the node, this current is coming out of the node, and Ix we were told to assume that it is coming into the node in this fashion. So Ix coming in is equal to 0.5 plus Iy. Whatever's coming into the node is equal to whatever is coming out of the node. So Ix plus 0.5 Ix. So Ix is coming into the node, 0.5 Ix is coming into the node. This is what we assume. Whatever is coming into a node is equal to what's coming out of the node. So Ix plus 0.5 Ix is equal to Iy. We will be able to solve for Ix in that case, since we know Iy. So if we solve for Ix as a value, and we know that this resistor is 10 ohms, right? If we solve for Ix and we find that it's a positive number, let's say, how much? 1 amp, for example, whatever it is. 2 amps? 2 amps. So Ix is equal to 2 amps. If Ix is equal to 2 amps, and I assumed Ix is flowing in this direction. So since Ix was assumed flowing in this direction, and this is a resistor, so it absorbs energy. So I know that the polarity of voltage is plus and minus. The current is coming into the positive polarity. Since I solved for Ix and I found it to be positive, then I know that the polarity of Vx is in this direction. Right? So if I know the polarity of Vx in this direction, I know that Ix is equal to 2, then and my resistance is equal to 10, so the voltage Vx is equal to I multiplied by R. So 2 times 10 is equal to 20, so you have 20 volts, Vx is equal to 20 volts. Now I go Kirchhoff voltage law. So minus Vs plus 20 plus 15 is equal to 0. And you can solve for Vs. Right? So let's see the solution on the second page. So like we did, we initially solved for Iy from knowledge of voltage and ohm and impedance of the resistor. And then we applied Kirchhoff's current law at this node, and we found Ix from that, which is equal to this sir. Because this is a source. Remember, sources, back to we said that any element, if current is coming out of the positive terminal, then it's a source or it's generating power. If it's coming into the positive terminal, then it is absorbing or consuming power. Right? So this is a source. It's a current source. So it would be a positive polarity. The current will coming out of the positive terminal for a source, battery or current source. Good question. So Ix we solved equal 2 amps, and because the Ix turned out to be positive as we said, then Vx polarity, we can define it in this way, and the value is equal to 10 times Ix, which is 20 volts, and then we're able to go around the loop and solve for Vs, which is equal to 35 volts in this case. Everybody's good with this? Okay. So we have a little bigger circuit, right? So solve for the voltage for the source voltage Vx in the following circuit. Same kind of problem here. So we were given what? We were given 1 amp flowing in this direction, and we were given a circuit that looks like this. So note the current in the 5 ohm is equal to 1. So we were given the current in this direction. So what is the polarity of voltage across the resistor? Positive on top, negative on the bottom. And this and this and this resistor, these are all in parallel, right? They share 2 nodes. Since any elements that share 2 nodes are in parallel. So that means that the voltage polarity across all of these 3 resistors and the voltage magnitude is the same. So what is the voltage magnitude across these 3 resistors? What is the voltage magnitude? Should be? Exactly. So for all 3 elements, again, these are in parallel. So let me see. I know more information about this one. So I know the resistance, I know the current. V equals I times R. So I multiply current multiplied by the resistance, so it's 5 volts. So and I know the polarity of it because of the direction of the current. So this also has 5 volts across it. This also has 5 volts across it because they are all in parallel. So if I know the voltage across the 10 ohm, do I know the current or not? So V equals IR. I know the voltage, I know the resistance, so I can find current. This is the same thing. I know the voltage, 5 volts, I know the resistance, so I can find the current. Right? So I know this current flowing in here, I know this current flowing in here, right? And all of these currents, this is all one big node, right? All of this is like one big node, right? One big junction in your circuit, right? In your fluid circuit, one big junction. There is flow on this side of the junction, from this port of the junction, flow from this port of the junction, flow from this port of the junction, flow from this port of the junction. So we take this one big node starting from here all the way into the end, and we know that anything coming into this node is going to equal to whatever's coming out of this node. We know the polarities of currents and voltages across these parallel elements. We were given because of this. This was provided to us here. So we know that current is coming out here is equal to what? V equals IR. So I is equal to V over R, right? Half, sorry, yeah. Half here, and then 1 here, and then 1 here, right? So this current is coming out, this current is coming out, this current is coming out. All of these are coming out of this node, right? We can assume that current is in this stage, in this node, in this branch is coming into the node. You can assume that, or you can assume the opposite. Does not really matter. But what you need to do after, what we will need to do is then add, give this a name, call this IX, for example. IX, call it IX, and then IX is coming into the node, for example, and all of these are coming out. So the sum of everything coming in plus everything coming out is equal to 0. So IX plus half plus 1 plus 1 is equal to 0, and you'll be able to solve for IX. If you solve for IX and you find that it's positive, what's the next thing you can do? You find the polarity across the resistor, because what you want to find is Vx, right? And I don't know Vx, go around this loop. I know that the voltage across this resistor is what? 5 volts, and I know its polarity, plus on top, minus on the bottom. But I'm trying to do KVL to find Vx, and I cannot, because I don't know what's the voltage polarity across the resistor. Is it opposing this voltage source or with the voltage source? It would depend on the direction of the current, right? So we will have to solve for current first. If we find that we assume current going in one direction, and we came up with a positive number for the IX, for this IR that's flowing through this resistor, 5 ohms, then we have defined the voltage polarity. So let's see. So same steps will follow. So we know a lot about these branches, the currents in these branches, from the information given to us about this resistor. So we know that everything coming in to this node is equal to everything coming out of this node. So whatever's coming in is assumed to be I3 in this case. So I3 is coming into the node is equal to I1 plus I2 plus 1 amp. So I3 is equal to I1 plus I2 plus 1 amp. And we will solve for I3. I3 we solve for as 2.5, a positive number. So what we assumed is correct. The direction, the polarity of I3 is now correct. There's nothing wrong with assuming I3 flowing in the other direction. If you do that, you will solve for I3 and it will be a negative number, right? Because it's going to be also coming out of the node. So in this case, you'll have I1 plus I2 plus 1 plus I3 is equal to 0. Right? And in that case, I3 would be a negative number. So you will in that case, you would know that you assumed the wrong polarity and you will flip. Right? We figured out that it was correct, the polarity we chose was correct, so I3 is in this direction. Since I3 is in this direction and this is a resistor, it's easy for us to define the polarity across this resistive load. So current is coming into the positive terminal. So we put the positive terminal here, negative terminal here. Now we can go around any of these loops. We can go around this loop, we can go around this loop, we can go around this big loop, whatever we want. Okay? So based on the direction of I3, we define the polarity of voltage across the left to 5 ohm resistor. And from Ohm's law, we know that this is a 5 ohm resistor. I know I3 is equal to 2.5, so the voltage is equal to 12.5 volts. And then I can go apply Kirchhoff voltage law around the loop. So starting from this node, I go around the loop. So minus Vx plus Vz, which is this voltage, right? Plus Vy, which is this voltage, the voltage across the parallel branches, is equal to 0. And we solve for our source voltage Vx. Okay? Yeah. That's the end of chapter 1. We'll go ahead and start chapter 2. Just a little more complicated circuit, more larger circuits. So more larger circuits, we'll come up with more interesting tools to help us simplify the circuits. That's all this chapter is about, really. So any questions on what we've discussed so far? Basic? Good. Again, when you start building larger circuits uh, of any type, electrical, fluid, whatever, you need to figure out pump pressures, you need to figure out flow rate. So you need to figure out ways to simplify, or you look at all the pressure drops across your system to be able to find how much pump pressure you need to push a certain flow rate. I mean, it's something you need to do in any discipline. So if you just keep thinking of analogies, you will appreciate what we're doing here, right? So for example, we have the series connection of resistors. So you have a flow line with many different restrictions, multiple restrictions in series, right? All of these restrictions are causing pressure drops, right? Requiring you to increase the pump pressure to be able to maintain a certain flow rate, right? So the resistors in series, they're summing up, they're adding up to each other, they're increasing the resistance to flow, and you would have to think of, okay, I have to sum up these pressure drops to be able to compensate them. So the idea of resistors in series is the same. So if you have 3 resistors in series, as you see here, these resistors will have the same current flowing through them. I mean, if you have a line with 3 restrictions, it's the same flow rate through the whole line, right? Except that if you want to maintain the same flow rate, these pressure drops are something you have to oppose. Figure out a way to overcome these pressure drops. So same thing with 3 resistors in series. Resistors in series have the same current flowing through them, but they will have different voltage drops across them, right? Depending on the size of the restriction, the pressure drop will be different. You want to find the equivalent pump that you need to pump to select, then you need to be able to sum up all the pressure drops, or here in this case, sum up all the voltage drops, so that you can select the proper pump, right? So here we do the same, but we sum up all the voltage. So this is a loop in this case, and what we would like to see is what is the equivalent resistance. This is my source. My source is seeing an equivalent resistance or impedance to flow of current. I would like to figure out how to calculate an equivalent value for that. If the resistors are in series, you simply add the resistors up. So the equivalent resistance is R1 plus R2 plus R3. Okay. How about if they're in parallel? You have a pipe and you have 3 outlets in parallel. Do you think that will increase? And each of these requires a certain flow rate in it. So you have a certain load, 3 loads with each requiring a certain flow rate. And all of these are in parallel. What will the total be? Definitely a higher flow rate than each individual flow rate. So basically each individual flow rate, you will add them, right, if they're in parallel. A pump here, a junction here. This is flow rate to your loads, hydraulic loads, right? These are there for a reason. These are loads you need to feed. And the loads typically define what flow rates they require, right? I mean, you need to feed your load with a certain flow rate at a certain pressure, right? So they typically define what you need to put in the system. And that's why we're always trying to go back and find Vx, right? We're always trying to go back and find the source voltage, right? Because typically the loads are known. You typically know that this process needs a certain flow rate to function, right? So how do you design the system that makes this process work is what you're working back towards, right? So these are all flow rates that you have defined. These dictate that the flow rate coming in here is equal to the sum of this flow rate plus this flow rate plus this flow rate, right? So if I would like to come up with an equivalent impedance or equivalent resistance for what the source is seeing, is it going to be equal to any of these, larger than these, smaller than these, any of these individual values? So for example, I have here 3 resistances, right? And I have, this is 1 ohm, 2 ohms, and 3 ohms. I want to find, and these are connected to my source here, my source is here. I want to come up with an equivalent resistance like I did for the series combination. Just from the physics, do you think that this equivalent resistance would be, what is the value of this equivalent resistance, approximately? Is it going to be equal to any of these elements, larger than any of these elements, or smaller than all of these elements? Smaller than all of the elements, right? Because it's going to require a certain flow. The equivalent one requires the flow rate, this larger flow rate. This larger flow rate is larger than any of these individual flow rates. And the pressure is the same. You're at the same node. It's the same pressure, same voltage, right? So same voltage and larger flow rate. What does that mean? Less resistance to the flow, right? So definitely this equivalent resistance will have to be less than any of the 3. But how much less? And that's how that's what the equation will come up with. So these are resistors in series. So we have an example on resistors in series here, and we derived it again. We derived the resistors in series equivalent resistance here by looking at what this resistor has current flowing through it. So a certain voltage drop, another voltage drop, another voltage drop. From KVL, we know that the voltage around the loop is equal to 0. So we start at this node, minus V plus V1 plus V2 plus V3 is equal to 0. So V is equal to V1 plus V2 plus V3. And we know each of the voltages are 1 times I, R2 times I. The current is the same, right, in these circuits. So we can rewrite Kirchhoff's voltage law as V equals summation of the resistances multiplied by I, which is now the equivalent resistance. So in this case, in the series case, we added them up. So in the series case, the equivalent resistance is larger than all of them, right? Some notes on series resistors, they have the same current. For series resistors, if one resistor is infinite, yes, if one resistor is open circuit, current is not going to flow, right? Any of the resistors is open circuit, current will not flow. Okay, resistors in parallel. Right? We went through the analogy and we want to find a similar equivalent resistance. We will find that the equivalent resistance in this case is equal to 1 over the inverse of each of these resistors. And we will prove it in the next slide. So this will definitely be smaller than any of these resistors. So let's look at the proof on the next slide. So these 3 parallel resistors will all have the same voltage across them. I agree? They're parallel elements, so they will have the same voltage across them. So this same voltage is equal to the source voltage in this case, right? So the source voltage is equal to across this one, also across this resistor, also across this resistor. So if we know V and we know each of these R's, then I also know the current in each of these branches, right? So I know the current here and current here and current here. So now everything is defined. So let's see what we can do from Ohm's law. I know that I1 is equal to V over R1. I2 is equal to V over R2. I3 is equal to V over R3. Then let's apply Kirchhoff's current law at this node up here. Whatever is coming into the node is equal to whatever is coming out of the node. So I is equal to I1 plus I2 plus I3. So we write this down and then we substitute with what we have here for I1 and I2 and I3. We will find that I is equal to, between parentheses, some value multiplied by V. And this is Ohm's law. V equals IR, right? I've just rewritten it. So in this case, the equivalent impedance is equal to what? So if I want to write Ohm's law, V equals IR, I will bring this on this side. So I'll divide it by, so 1 over this parenthesis is equal to V. 1 over this parenthesis multiplied by R is equal to V. So this would be this. 1 over this is equal to the equivalent resistance seen by the source. Okay? You okay with this? So you can, if you have two resistors in parallel, you can put a common denominator and simplify, and you'll find that the equivalent resistance of equivalent resistance for two parallel resistors is equal to the multiplication of the two over the sum of the two. Just some rearranging there. Of course, for parallel resistors, if one or more resistors is zero, there's a short circuit. Equivalent resistance is zero, right? So I have a short circuit. Short circuit means what? 0 volts. Right? I take a resistor, I put a wire around. Then, again, you can consider that short circuit as another resistor, right? That has a value of 0, right? So, and we know that the equivalent resistance is smaller than any of the ones that are existing in parallel branches. So, equivalent resistance in that case is 0, right? So, anytime you have a short circuit or in parallel with any part of the circuit, then that short circuit is what's going to win, right? Current will flow into the short circuit, the least impedance, right? Here's an example where we have a combination of some series and parallel resistors, which is what we have in real life, right? You don't have series only, or you don't have parallel only. You always have a combination of them, and you will be asked to simplify these circuits to solve the system. So we have a resistor network here. This is the original resistor network. You want to find the equivalent resistance for the following network. Find the equivalent resistance seen by the source, right? So these two are in series. So we find the equivalent by adding them up, right? So we add them up, and so this is 15 and 5, that's 20. And then what? How do we find the equivalent resistance here? These two are in parallel, and then after you find the value that's in parallel, then that equivalent value is in series with this, right? So these two are in parallel. It's 10 ohms, 20 ohms and 20 ohms. 20 times 20 divided by 40, right? R1 times R2 divided by R1 plus R2. So in this case, the equivalent resistance is 10 ohms, right? And 20 times 20 divided by 40, right? So 400 divided by 40 is 10. So now this is the equivalent of the parallel branch, and then you have one resistor left here. These two are in series, it's 10 and 10, the equivalent is 20 ohms. Yes, ma'am. Just a wire. Just a wire across. Just a wire. Right? So they do the math for us here, but basically went through it, right? So this will help us do what? This will help us now. Let's say I ask you to find the current drawn from the source, right? You would have had to go through this math, this logic, because let's say I give you the source is 10 volts. If I give you a source equal to 10 volts, I want you to tell me what current is being drawn from that source. So you want to select a battery to run this circuit with. So you will have to do this simplification of the circuit to come up with the equivalent value of resistance. So you can put it across let's say 20 volt battery, and this is a 20 ohm resistor. So you know now that the source current is 1 amp, right? So now 1 amp is coming in here. You know that, and that same 1 amp is flowing into this circuit, right? And then if I tell you, okay, what is the current in this branch here? So you found the source current, and then you went one step back, and you know that the source current is flowing here. I asked you what is the current flowing in this resistor. what would you have to do? Go one more step back. Expand again. I know now this current coming into this 10 ohm resistor. I know this current coming into this 10 ohm resistor. Right? It's going to be distributed between these two. These two happen to have the same resistances. So 10 amp coming in will be divided among them equally. Right? But another way to do it is what? Is if I know 10 amps is 1 amp is coming in, and I want to know what current is flowing into this branch or this branch. I mean, assuming they were different values. Here it's easy, okay, because they're the same value. If they were different values, how would you approach it? They are in parallel, right? So I know that the voltage across them is equal. So if I go back to this circuit, I know that the voltage across this parallel combination is equal to the voltage across this equivalent resistor, right? So I know current coming in here is 1 amp. 1 amp times 10 is 10 volts. So I will know 10 volts is across these two resistors which are in parallel. So now if they are different values, I don't care, right? This is 1 ohm, 10 ohm, this does not really matter. I know that the voltage across them is 10 volts. And you're given their impedances from your R equivalent calculation. So you know this is 10 volts divided by 1 ohm. So this is 10 amps. And the other branch is 10 ohms. So 10 volts divided by 10 ohms in that case will be 1 amp. So one branch will have 10 amps, one branch will have 1 amp. Right? So everybody is okay with this? The idea of, so you will always have to go and simplify and group things up, and then go back again sometimes to find different requirements that you're asked to do. Okay? More examples here. What do we do? These are 4 different networks. So how do I start thinking? I want to find the equivalent resistance across my source. For this, how do I start thinking? Sorry, I forgot the list of names. If I have the names, I will know your name, but Sally. Okay, what do I do? How do I find the equivalent resistance? Just the process. I don't want the numbers. These 3 are in parallel, so I'll find the equivalent resistance. This times this times this. Oh, sorry. This times this above on the sum of them. And this, then the combination here will be parallel with this as well. So you take the R equivalent multiplied by 6 divided by the R equivalent plus 6. So you find the equivalent parallel combination, right? Or you do 1 over 6 plus 1 over 3 plus 1 over 2, right? So you find the equivalent parallel combination, and then it's in series with this, so you just add it. How about this? Sorry, if I have the list, I know it. I know the mechanical guy, he sits here. I know I know these 2 Muhammadis, they're not cousins, but I know which one comes in the list first, but I did not bring the list today, sorry. So, okay, how do I approach this? Yes? Yeah. Sure. So R3 and R4, you find the parallel equivalent resistance. And then you add that parallel equivalent resistance to R2. You will find the equivalent resistance of now these 2 parallel with this series. And then you place it in parallel with this R1. Okay? Same thing here. These 2 are in parallel, and then these 2 are in parallel. So you find the parallel combination for these, find the parallel combination for these, and then the equivalent is this in series with this. Here it's the same. These 2 are in series, R1 and R2 are in series. Add them up, and then the sum is parallel to R3. Right? So what's the sum here? What's the equivalent resistance for this? It's already written here. But it's, again, these 2 are, this is 2K and this is 1K. 1 kilo ohm, so this is the sum is 3 kilo ohm. 3 kilo ohm and 3 kilo ohm, the equivalent is 1.5. Always half of them equal to each other. Right? So 3 times 3 divided by 6. Okay. So I just talk about the process that we just went through to solve these circuits. So please read that. And then there are just more examples here. So yes, ma'am. Part B, the back, this last one. Okay, so let's see. So we have 3 ohms in parallel with 6 ohms. So 6 times 3, 18, divided by 9 is 2, right? So the equivalent of the R3 and R4 is 2 ohms. 2 ohms is in series with 8, right? So 2 plus 8 is 10. 10 now is in parallel with the R1, so 10 is in parallel with 10. So we said when they're equal to each other, the equivalent is half. So it's 5 ohms. Okay? Right? So 3 and 6, 3 times 6, 18 divided by 9 is 2, 2 plus 8 is 10. 10, which is the equivalent resistance for this R2, R3, and R4, is in parallel with another 10. So 10 times 10 divided by 10. Okay, so we'll stop here and continue next time.